Thanks for coming out, everybody. I have some news. This is actually going to be our last one for this term. Unfortunately, due to the scheduling conflict, the one we had for next week is going to be canceled. Okay. But hopefully we'll try and see about getting something started up in the new year. Usually we only do these through the summer and the fall term, but since it's 3 of us now in the facility, it's a little less urgent. So maybe we'll try and get some after Christmas. So yeah, as far as announcements, I think that's it. So today we have Erin Diel, who is our new imaging specialist. She's been in the facility since October. Probably a lot of you have met her. She's fantastic, and she's made my life much more enjoyable. So we're very happy to have her. And she's going to talk to us today about Fleetwood Mac.
Yeah,
I just learned.
Yeah, so I don't know if anyone got the reference, but this title, Time Passes Spell on You, is a reference to a Fleetwood Mac lyric or a Silver Spring, I would recommend it. But the real topic of the talk today is about the time that you take to acquire your image. And the reason that I wanted to talk about this today is because a lot of your choices that you make, from the microscope that you choose to image from or any of your acquisition parameters, can dramatically change the time that it takes for you to actually acquire that image. And that's not just important for your personal time, but it also pretty directly relates to the quality of your image and the kinds of data you can analyze from that image. And so I think it's actually, these are a series of important decisions that you'll make when you set up your image acquisition tools that will change the quality of your data and the time that you spend at the microscope. So my goal for this lecture is to talk both about some basic principles, but also some practical advice going through the Zen software and pointing out locations where you can change certain parameters and how they change your acquisition time. And so we'll start by talking about sampling theory. So the idea is that you have some signal that you want to measure. And so here we're looking at some intensity that changes with time. And so this is the real continuous signal that you're wanting to measure. And so let's say we start by measuring it at 3 points. We get an output that doesn't look much like our original signal. If we only sampled it these 3 times, then we would get a pretty inaccurate view of what was actually happening in our sample. Okay, so what if we sample a few more times? Now we start to get a more accurate picture of what's happening. We start to see some of these oscillations, but it's not perfectly recapitulating what the real signal was. So the question is, how do you know when you've sampled enough? More sampling is great, it takes more time, but how do you know when you've sampled enough? And this is an idea that had been talked about for decades before this formal proof was actually published. But the idea is that if you have some function, some continuous signal, that is band limited, meaning it has no frequencies higher than a certain frequency they're calling W here, then it is completely determined by giving its ordinates, or taking measurements, at points that are spaced 1/2 W seconds apart. So essentially you have some signal that you want to measure, and you need to measure it at double the frequency that you're interested in. So if you're watching cells move, or you're watching GCamp, then if there's some frequency that you're interested in your signal, then you need to sample at double that rate. And instead of W here, we have our frequency of interest. And the trouble is that sometimes you don't know what that frequency is. You don't actually know how fast your cells are going to be moving, or how quickly your protein is produced or degraded. And so you can start with this F being, some hypothesized frequency that you think should be true. But the other thing to look out for is, like in the previous example, if you measure on a few different experiments, or if you measure and your signal, the trace of what you see in your signal is changing, you don't get some accurate reproducible fit for how your signal is changing, then that could be a signal that you've undersampled. That could be a sign that you've undersampled your data. And so some of us are not looking at some dynamic signal. So you're thinking, well, I'm not looking at GCamp changing or cells moving. I'm just looking at a structure in a single static image. And this rule is still important for you because there are the same rules apply for spatial sampling and not just temporal sampling. And even if you're taking some time series, each of your individual frames needs to follow these rules for spatial sampling. So here's an example where you have an image of two structures, two circles, and you can see that when I have a small pixel size, I can see that there's clearly two objects here. But if I increase my pixel size, I can still probably differentiate them here. But if my pixels get too large, then I can no longer see that I have these two structures here. And so I'm undersampling spatially. And now I don't want to imply that pixels give you your spatial resolution of your microscope. We've learned this in previous Lunch and Learn lectures from Doug, that the resolution of your microscope is set by the wavelength of light you use and the numerical aperture of your objective. And so here we see depicted 3 different objectives with different numerical apertures because they're collecting a different size cone of light. And so this is what's fundamentally setting the resolution of your microscope itself, but you can change what you're able to see by undersampling your microscope. So achieving this optimal resolution does depend on proper sampling. So let's say that this is the optimal resolution of our microscope. If we undersample, we don't achieve that optimal resolution. And so I want to talk about spatial sampling and how it relates to imaging time in the context of 2 broad classes of systems. The first is using point scanning, where you are generating your image by scanning a point of light across your sample, and that light is going to a detector, say a PMT. And so you're reading out your image dot by dot. And so you have a lot of flexibility over how you sample and how you generate that image. But I also want to talk about camera-based systems where, say, you're illuminating a whole field of view with a widefield scope or something like a light sheet, and you're taking a picture with a camera. And there's a little bit less flexibility in changing your sampling, but we'll talk about how you can change your sampling even in camera-based systems. So let's start with these point scanning systems where you're creating your image point by point using your detector. So I've already told you that achieving optimal resolution depends on proper sampling. So how do we change our sampling, our spatial sampling with a point scanning microscope? So you can change your frame size to change your pixel size. So here's a window that you might be familiar with from Zen. It's your acquisition mode window where you can set your objective, your frame size, your scan speed, and a number of different parameters that we'll go through. So first we have our objective here. We're starting with a 10x objective that has a numerical aperture of 0.3. And we can set the frame size. So right now it's set at 512 by 512. I think if you choose your 10x objective and do a smart setup, it will auto set this at 512 by 512. What you might not have looked at before is that it also reports your pixel size. The pixel size right now is 1.66 microns. But we can change this. If we change to a 1024 by 1024 image, then now your pixel size is 0.83 microns. So we've changed our spatial sampling by changing the number of pixels that we have in our image. You can also optimize this. So within Zen, there's a button that says optimal. And so if we press it, then it will change the frame size of our image, thus the pixel size of our image, to be optimal. We'll talk about what that means, but you can see that now our frame size is quite large, 2140 by 2140, and now our pixel size is 0.4 microns. Another thing to note is that our scan time just went up to almost 17 seconds. So you don't get pixels for free, but this is what this optimal button is used for, is to optimize your spatial sampling. So what does that mean? It's made it optimal. How did they figure out that setting? So if you hover over this optimal button, what it says is that it's setting your optimal frame size so that your XY resolution, taking into account your XY resolution for Nyquist sampling. So those sampling rules that I talked about where you need to sample at double the frequency of what you're interested in, it uses that rule to set your pixel size so that it's appropriate for the resolution given the objective that you've chosen. So let's check the math. We know that the resolution of our microscope is set by the wavelength and numerical aperture of our objective, and so we can find our numerical aperture here, and we can put that into our equation. We can also say that we're using a 48 laser to image our sample. And so the resolution given this system is 992 nanometers, or almost a micron. And our pixel size that it has created for us by pressing this optimal button is 400 nanometers. And so we can check, is this sampling rate appropriate for the resolution of our microscope? So we know that our sampling rate should be greater than 2 times the rate of what we want to see. And what we want to see is this resolution. So I'm setting this as our desired frequency to observe, and this as our sampling rate. And so let's see if this n is equal to or greater than 2, and in fact it is, so it's around 2.5. So what Zen is doing when you press this optimal button is satisfying this Nyquist criterion. So setting your sampling rate at double the rate of what we want to visualize, which in this case is your optimal resolution. Okay, so what if we go to a higher NA objective? So we want even better resolution. If you're looking at some fine structure, you probably used maybe the 40x or 63x objectives on some of our point scanning microscopes. So here we have a 40x objective, and the numerical aperture is 1.3. So we've significantly increased the NA of our objective. And what you can see is that even starting with this 512 by 512 frame size, that's where we started with the 10x as well, we already have a pixel size of 0.4 microns, similar to the pixel size here in the 10x objective where we had to optimize our frame size. So going up to a higher NA objective allows you to get smaller pixels. When your higher magnification, higher NA objective gives you smaller pixels when you have a smaller frame size. But let's optimize, you don't get that for free though. You can't just go up in magnification and get resolution for free. You also decrease your image size. So here we were scanning 850 by 850 microns, and here we're only scanning a little bit over 200 microns. And so great, you can scan a smaller frame size and get smaller pixels, but you aren't scanning over such a large area. So if you have some big structure that you're trying to image, then you have to do a tile image, which also adds to your acquisition time. So let's optimize this for this objective now. So we'll press our optimal button. We see that our pixel size goes up, our frame size goes up dramatically to over 2,000 by 2,000 pixels. But now our pixel size is quite small. It's 0.09 microns. So are we, again, satisfying this Nyquist criterion? And yes, we are. If we do the math again, we get the same, and it's approximately 2.5. So we're more than double sampling in order to give us the resolution that we want from this microscope. So this is the resolution we can achieve, and so we're sampling at more than double that frequency. I also wanted to point out that there is another optimal button if you have a Z-stack. So if you're not just imaging a single frame, but you're imaging multiple frames across different Z positions, then you can see you set your first and your last points of your Z-stack, and then you can hit this optimal button, which will give you optimal spacing of those Z sections as well. And if we hover over this button, it's setting your step size so that there's an overlap where you're double sampling given the depth of field of your objective or the size of your pinhole in a confocal system. And so using this optimal button and this optimal button, you will be satisfying the Nyquist criterion in XY and also in Z. So some of you might be looking at this and thinking, I never press the optimal button. I never use that many pixels. That would take forever to scan that much. So you can see that if we press this optimal button, we have 2300 by 2300 pixels. It's now taking 17.58 seconds to acquire a single frame. So if you have a big Z-stack, if you're doing a big tile, if you have multiple tracks, it's going to take some time. It's not just 1 or 2 seconds for a single frame. So how can you balance this optimal sampling and speed? One way is you can crop your scan area to decrease your frame size and scan time while you maintain your sampling rate. So in this case, we've kept our pixel size at 0.09 microns, but we've shrunk our frame size because we've actually cropped our field of view. So we're scanning over a sort of sub-field within that given field of view. And so you can achieve the same resolution, but your frame size is actually smaller, and you can see your scan time is a little under 4.5 seconds. So we've really improved how fast we're imaging a single frame, and if you're imaging a small structure, then this is perfect. You don't have to image such a large area. There's a way that you can, sorry, Erin was pointing to those things. There's also a way that you can do this while viewing your image itself. Let's say this is your field of view, and you want to crop it. You want to be able to see your cells and say, I want to crop it around these cells here. That's what I really want to image. I want to image the center of this pinwheel, let's say. And so you can hit this crop button, and your field of view, your new cropped field of view, will appear on your image, and you can adjust it accordingly, knowing what is in your image underneath it. And then when you hit live again, it will be that cropped field of view. So that's a really nice function. But something to keep in mind, and this is a helpful slide that Christian created, our new embedded device specialist. He noted that you can see that on this crop function, on this box, you have some red lines and one single blue line. And you always want to make sure that this blue line is the longest dimension, because you could be scanning a square, but you can also change your crop region so that it's, say, a rectangle. And so you want to make sure this blue line is your longest dimension, because it changes how it actually scans across it. You can see here it's doing a fewer number of passes, but they're each individually longer in X. Whereas here it's having to do many more passes, and that turnaround time makes that scan take a longer time, despite the fact that you're imaging the same area. So that's one easy way to make your image acquisition faster without changing anything about what you're imaging underneath it. Okay, so another thing you can do if you don't want to take 18 seconds to acquire a single frame is to sacrifice optimal resolution. So instead of having my frame size be this optimal condition, I'm just going to stick with 1024 by 1024. My pixel size is not gigantic, it's 0.21. A lot of things that you might be interested in quantifying will be easily quantified using that pixel size. So if you're counting cell bodies, you can definitely count a cell body. If you're sampling every 0.21 microns, you're probably still oversampling in that case. But then the question is, should you change objectives? Why are you using such a high NA objective if you're not sampling at a rate that's appropriate for that objective's resolution? Because what I told you before is that your field of view decreases, right? If we look at our image size, this field of view is around 200 by 200 microns, where with the 10x it was over 800 microns. So you decreased your field of view by a factor of your magnification squared. So that's not great. And also, if you don't change anything else about the objective, your brightness is similarly going to decrease by a factor of your magnification squared. But if you increase the numerical aperture of your objective, which in many cases as we go to higher magnifications, we also notice the NA gets higher, the brightness is actually increasing at a rate of the numerical aperture to the 4th power, whereas it's decreasing with the magnification to the 2nd. So here are some examples of a few different objectives with different magnifications and numerical apertures. And you can see that as we go to, say, this 40x, compared to some of our lower magnification objectives, these are the relative brightnesses. And you can see that, in fact, your brightness has increased a lot because of your numerical aperture increasing, despite the fact that your magnification is increased. But there is a limit to that. If you go up further to some of these higher magnification objectives, we have some 63x objectives, some 100x objectives, you can see that you are starting to sacrifice some brightness because you aren't getting as big of an increase in your numerical aperture as you are losing brightness from your increased magnification. And so if you're saying, well, I need to use the 63x objective because it has 1.4 NA instead of 1.3 NA, you should think about, are you actually using the resolution provided by that numerical aperture because you are losing brightness, you are sacrificing some of your signal. And especially if you're going to a 100x objective, I think we have some 100x and 63x objectives that have the same numerical aperture, and so in those cases, you're just losing your brightness. And so be sure to think about, how much am I actually sampling? How big is my pixel size? And do I really need that high of a magnification objective, or can I balance the resolution that I need with the magnification of your objective? And then finally, you can just increase your, decrease your imaging time, scan faster, just by increasing your scan speed, which decreases your pixel dwell time. So this seems too good to be true. In order to image faster, you just image faster, but it is true. You can increase your scan speed. So here, we're set at a speed of 6. Your scan time is 17.5 seconds. And if we hit this maximum button, maximize scan speed, then we go up to a speed of 8, and our scan time is now 7 seconds. So that seems great. We just have our scan time and image the same pixel size, the same frame size. There is a limit to this. If you were on, say, a 512 by 512 frame size, your frame size is smaller, you can see that now your maximum scan speed is 10 instead of previously it was 8. So it won't allow you to scan as fast as your pixel size gets smaller and smaller, because it can't accurately scan that fast with across those smaller pixels. So why wouldn't we always do this? We have all of the sampling that we want. We have our perfect pixel size. So why don't we just scan faster? And the reason is because as you scan faster, you get more noise. So you're decreasing the dwell time over a single pixel. And so you'll notice if you scan faster and faster, your image will look more noisy. So what is noise? We always talk about signal-noise ratio. We want more signal, we want less noise. So where is this noise actually coming from when we scan more quickly? The first example of noise is Poisson or shot noise. And this comes from the fact that you're counting photons at a detector. Your photons are arriving at a detector. And because that's a stochastic process, it follows Poisson counting statistics. So sometimes you release 10 photons or 100 photons, and there's some mean to that distribution, but there's some also noise in that distribution. So we can calculate what this Poisson noise is, and it's equal to the square root of the number of events. And so what are the events that we're talking about here? It's the number of photons. And so if we want to calculate our signal-to-noise ratio, what we can see is that our signal is the number of photons. The noise is the square root of the number of photons, and so your signal-noise ratio reduces to the square root of the number of photons. So the more photons you have, you will increase your signal-to-noise ratio. And so you can get that in a lot of ways. One is to, at the sample prep side, have a brighter signal to start with. But another way you can get this is scanning more slowly, dwelling over a single pixel for or a point of your sample for a longer period of time, and thus collecting more signal. And so that will increase your signal-to-noise ratio. Another kind of noise is not dependent on your sample. It's dark noise, which is the thermal emission of electrons without any arrival of photons. So if you were looking at the signal coming off your detector, where you weren't putting any light in, that would be your dark noise, is the sort of graininess that you would see. The good news with this noise is that I've already described ways that they can decrease with longer pixel dwell time. In the case of shot noise, as you accumulate more signal, your signal-to-noise ratio goes up. Your dark noise will also decrease with longer pixel dwell times because your signal will accumulate faster than this dark noise will accumulate. The other way that you can improve your signal-to-noise ratio is with averaging. And the reason for that is because your signal should be in the same spot every time you take you scan across your field of view, but your noise is going to be random. And so if you average, the noise will average out, whereas your signal will remain. And so you can average, again, within the Zen software. So there's this averaging panel here, where you can set the number of times you want to average. So do you want to take 2 images? Do you want to take 4? Do you want to take 8 and average across any number of them? You can also change the way that you average. So because this is a point scanning system where we're scanning point by point, you can, in this example, it's in the line mode, which means it's going to scan every line twice and then move to the next line and scan it twice, or however many times that you want to average. But you can also switch this to frame mode, where it will scan the entire frame, and then it will scan another one, and it will average those 2. It will scan 4 and average those 4. And there are different motivations for using these different modes. Averaging isn't always possible. Let's say you're looking at some live cells, maybe they're moving. If you average and they're moving at a rate that's faster than your scan time, then you're just going to be blurring your image. If they're moving a bit more slowly, that could motivate a line scan because you're scanning over the same region of the image, and then by the time you've gotten to the bottom, that cell has moved, but you're scanning a different cell, and so you could motivate yourself to use a line scan if the cells weren't moving too quickly or whatever process wasn't changing too quickly. Another reason that you might choose line over frame averaging is because you can imagine by the time you've gotten to the bottom of your frame and you go back to the beginning, things might have shifted in some way, or maybe you didn't go exactly back to the correct point in your image, and so it looks like the signal to noise has gotten better, but in fact what you've induced is a little bit of blurring. And so you want to be careful that what you're creating with averaging is really an increase in signal to noise instead of just a blurring of your image. So this is a panel that you can make use of if you want to improve some of your signal to noise, scan a little bit more quickly, but do averaging instead of lowering your scan speed. So those are 2 methods to overall increase your pixel dwell time. Either in one moment you lower your scan speed, or imaging multiple times and then averaging. So why don't we always do this? Great, we want high signal to noise. We should always average. We should scan really slow and average 16 times and get beautiful signal to noise. Again, there is a trade-off, and the trade-off is bleaching. So any time that you spend with light on your sample increases the bleaching of that sample. So a given fluorescent molecule has some lifetime of the number of cycles of photon absorption and emission that it can go through before you'll structurally change it, and it will no longer fluoresce in the way that you want it to. And there are a number of factors that will generate these cycles of absorption and emission. Of course, if you have higher laser power, that can lead to bleaching. If you have a longer dwell time, it's going through more of these cycles. If you are averaging, so you're imaging again and again and again and averaging together, or you're doing a time lapse similar to averaging, imaging again and again and again. All of these will cause your fluorescent molecule to go through this cycle of absorption and emission, and so limiting as much as possible how much you're imaging will limit the bleaching of your sample. So you really have to think about which one of these is really optimizing the signal that you get so that you're not bleaching your sample unnecessarily. And there are a couple of conditions where you really want to be careful with this. The first is live cell imaging, because not only can, say, a high laser power bleach your fluorophores, but it also might damage your cells themselves. Also, if you have oxygen present in your sample, that can increase this photo bleaching. And then finally, with Z-stacks, you want to be careful because even as you're looking at your image frame by frame, you have to remember that your light is illuminating planes above and below that Z-plane that you're actually visualizing in that moment. And so by the time you get to the end of your Z-stack, you've actually sent light to other planes that you haven't even been imaging. And so if you do a really slow scan time across many, many Z-planes, then as you're acquiring that whole Z-stack, you're bleaching your sample, not just when you're scanning your individual plane. You're not just scanning that local environment that you're visualizing on your screen, you're bleaching above and below that plane as well. And so these are a couple of conditions where you might be more strict with how much light you're sending to your sample. Okay, so this is what we've gone over so far. First, just the ideas of sampling theory, the idea that the Nyquist criterion is that you should be sampling at double the rate of whatever you want to visualize in your sample. And I've given you some examples of things you can change in your acquisition using the example of a point scanning microscope and how those influence your scan speed. So now I just want to talk next about using a camera-based system and how we can apply a few of these concepts in a similar way. So, this is what we were talking about before, a point scanning system where you're imaging, you're detecting something from your sample point by point. But with a camera-based system, you're illuminating, say, a whole field of view, and then you're taking an image with the camera. And so you don't have as much flexibility on changing, say, your pixel array, your frame size that you're taking because you have some given number of pixels in your camera. So here's an example of two acquisitions using our AxioZoom widefield microscope in the facility. And you can see that both of these acquisitions, this is the AxioZoom, both of these acquisitions have the same image size in pixels. So we're using this 1200 by 1200 grid of pixels to image our field of view. But they're drastically different in the size of those pixels. So in this case, each pixel is 15.71 microns, but in this case, the pixel size is under 1 micron. So how did we achieve that with the same imaging system? Well, we increased our zoom. So in this case, the total magnification is 7, and in this case, the total magnification is 112. So if you have the same array of pixels and you zoom in on a smaller area of your sample, then you effectively decreased your pixel size because you're imaging a smaller area on the same array of 1200 by 1200 pixels. And so this is a way on a camera-based system that you can change your pixel size even if you're limited in your flexibility of changing the size of the frame in the first place. But we are similarly limited by the signal to noise ratios. So you want to maximize your signal as you change your zoom. You might change the exposure time. So instead of changing your scan speed, in this case we're just imaging one field of view at a time, so we're not scanning anything, but we might change our exposure time from 10 milliseconds to 150 milliseconds to get more signal. And we would still have some noise. So we would have the same problem of Poisson noise or dark noise, in this case from our camera. And so we would still need to balance our signal to noise by changing exposure time and thinking about the sources of noise from our sample. And similarly, doing longer exposure times would increase the rate of bleaching our fluorophore. So we have the same balances as with the point scanning system. It's just the way that we change our pixel dwell time is now exposure time, and changing your pixel size is not so flexible, but you can zoom in and out to get a change in your spatial sampling the same way that we did with the point scanning system. Okay, so I just want to talk briefly about deconvolution. I'm not going to go through deconvolution because there's a whole lecture on it from Sven, our previous embedded sci specialist. This is on our YouTube channel, and I encourage you to check it out because it's a really great explanation of deconvolution, but also he goes through particular settings under the processing tab in Zen that you can use for deconvolution. So I think it's very helpful. But I wanted to bring it up because it's a case where you can sort of break the rules that we've been talking about. So the first is that you might want to increase your sampling beyond the Nyquist criterion. So sometimes you can double the sampling in X, Y, and in Z, and then do a deconvolution to actually improve the resolution. Or you can use normal Nyquist sampling and maybe have a noisy acquisition. So scan really fast, have shorter pixel dwell times, and you can use deconvolution to increase your, improve your signal to noise ratios despite that fast scan time. So if you are interested, you can check out this lecture on YouTube. And so I wanted to finish by talking about multi-channel acquisitions because a lot of us are not just imaging a single color, and so we have to think about how we image our green and red and orange fluorophores in the same sample and how that influences the time of our acquisition. So some of you might have used this great tool, this smart setup tool, which allows you to put in fluorescent molecules that you're using. So in this case, I put in 4 Alexa4 dyes. It has a big library of all these dyes and their excitation and emission spectra. And then it will come up with a few different schemes for you to image. And what you'll notice is that it has this bar here that says speed. And so you can see how fast each of these schemes actually are. So in this case, we're imaging everything at the same time. So we have a single, what they call track. So we're going to set up the light path and we're going to image all 4 fluorophores at the same time. Or we can separate them out into individual tracks. So we still have 4 colors, but we're going to change something about the light path in each of those tracks, and that's why they are separated from one another. Or we can do some compromise where we have 2 per track. And so each of these is going to take a different amount of time. This one is going to be the slowest, and this one is going to be the fastest. But you're sacrificing something in being able to scan everything together and go really fast, and that's represented here in this crosstalk value or bleed through. So if you're imaging everything at the same time, then you have all of your, let's see, these 4 laser lines that excite these 4 molecules on at the same time. And so you might get some bleed through between the channels. And so if you want to fully separate everything and limit the amount of crosstalk, then you might want to separate them out into 4 or 2 tracks. But if you want to image as fast as possible and you can deal with a little bit of bleed through, then this is your faster option. And so let's look at what it actually creates if we choose this fastest option. So what we can see is that we have a single track, a single light path that describes that track, because we're not going to be changing anything, we're imaging everything at the same time. And we can see that we're sending different chunks of the emission to 4 separate detectors, and we have, probably hard to tell, but we have 4 laser lines on here to excite our 4 fluorophores. And this is possible because in this scenario, we do have 4 detectors to send our light to, and we can pretty finely control how we, what wavelengths of light we collect from this emission spectrum. So you can move these slider bars pretty finely to say, I want 5 more or 10 more nanometers on this side or this side of the emission spectrum. And so you can collect 4 fluorophores pretty easily because you have very flexible collection optics to decide what wavelengths are going where. But in some systems, this is not so easy. So this is an example from the 700 microscope that some of you might have used. And in this case, you only have 2 PMTs to send your signal to, and so you can only image your 2 channels at one time. And the way that you separate your 2 channels is with this differentially coded dichroic that can move in space to separate either at this point or this point or this point or this point wavelengths above and below to 2 separate detectors. And then we have some additional cleanup short pass and long pass filters on either side to send our light to 2 different detectors. So given the differences in the way that we're filtering light and sending it to different detectors, in this case we have to separate out into 2 tracks because we only have 2 detectors. So we can't image all 4 channels at the same time, but we can separate them out into 2 different tracks. So if you do have 2 different tracks, how do you image them in an efficient way? So if you click on your track switching drop-down menu, what you can see is that you have a few different options of when you switch tracks. One option is switching them every line. So we're back in a point scanning regime where you can scan line by line, and in an individual line you can scan it twice, and each time you scan it you're switching on and off the appropriate laser line. So you're imaging track 1 and having your 488 and 633 lasers on, and then you're switching to track 2. this is only possible if the only change you're making is switching laser lines. It won't let you switch every line if you have to move any hardware. If you have to move hardware, then you can do this frame option. So you scan a whole frame in one track, and then you scan your next track in a subsequent frame. This can be okay if you're not doing a really large acquisition, say a really large Z-stack. It won't be too slow. But it starts to become a problem if you have a bigger acquisition. You're doing a really big Z-stack, and maybe you're tiling, and in each of those tiles you have a Z-stack. Switching every frame actually starts to become very slow, especially if you're moving hardware in between those tracks. And so we can recommend that you try this switching every Z-stack option. And so in that case, it's taking an entire Z-stack with one set of settings in your light path, and then it's taking the next track, again, a whole Z-stack. And this can be a huge time saver because it's less mechanical switching time. So you want to be spending time at the microscope scanning rather than moving parts around. So you want to limit any of that mechanical movement and just have the scan time that we referenced in our original views of Zen. That should really be the major contributor to how long your total acquisition takes. So I sort of described this as a less flexible option because you have fewer detectors and you have some preset short pass and long pass filters. You can't finally set what parts of your emission spectrum you're actually collecting. And that is certainly true. These preset short pass, long pass filters are what they are. If you want it to be a long pass 10 nanometers different, you just have to buy a different long pass filter. You can't just change it here. But I don't want to imply that filter sets are always cumbersome and not helpful. There are some pretty nice filter sets that can get you really quick imaging. And so I wanted to go over a set of filter cubes that can make a big difference in some image acquisition. So in this case, a little bit more complicated than just a long pass or short pass filter. This is a depiction of a fluorescence filter cube where you have some incoming light source and you have an excitation filter here. And then you have your dichroic that sends your excitation light to your sample and lets your emission light through. And then you have an additional emission filter at the other end. And so this is a depiction of one of these. This is a GFP filter cube. And you can see that it has a band for your emission filter and, your excitation filter and your emission filter here. But they can get even more complex. So here is an example of a triple band pass filter cube where you have 3 notches for your excitation light and 3 notches for your emission light. And so you can keep the same filter cube in place, and you wouldn't have to have an individual cube for GFP and an individual cube for DAPI and an individual cube for TV tomato or whatever other signals you have. You can keep the same filter cube in place, and there are even quadruple band pass filters. Some of you might have used the quad band pass filter that we have in the AxioScan, for example, to scan 4 channels very quickly. And so you can have pretty complex filters, even though they're set and the wavelengths that they transmit are just set. This excitation band and emission band are set, but they can be pretty great controls of your light, especially some of these triple band pass or quad band pass options. So I wanted to finish just with this impression of some of the concepts that we've talked about. So this is a triangle of things that you're trying to optimize. So you have image speed, you have your sensitivity, and you have your resolution. And so a lot of the parameters that I've talked about today, I've highlighted that, once you change your frame size to be optimal, your pixel size to be as small as possible, well, then you're scanning really slowly. Well, what if we scan faster? Well, then your signal to noise ratio goes down. So obviously these things are all in a balance. And so I don't mean to say that any of the individual parameters that I talked about all need to be optimized, because that's impossible. So I hope that this has given you some tools on how you can play around with those settings for your individual sample and your individual imaging needs to understand which one of these needs to be optimized for you. And if you're confused and you have a sample and you want to know how to optimize any one of these without sacrificing too much in the other dimension, we're always happy to help. So don't think that your image acquisition isn't perfect because you haven't optimized all of these things, but hopefully you learned a little bit about how to balance between them. So thank you, and I'll take any questions.
Is there any kind of rule or calibration for pixel dwell time and how it relates to teaching? Because I find I always just try to be careful and not leave my sample.
Yeah, so this is something that I've tried to read a lot about, and there's not a lot of satisfying answers. And I think one problem is that depending on what your fluorescent molecule is, that lifetime that I talked about, the number of cycles that it can go through, it can differ by orders of magnitude. And so certain fluorescent molecules you can image for so long that you would have a much longer pixel dwell time and you wouldn't care about it. And then other more sensitive, worse dyes, you would want to keep your pixel dwell time super short. So I think that's why it's hard to give, oh, this is the optimal number. You'll notice in Zen, as you change your frame size, it will auto adjust your speed. And that has to do a little bit with how accurately it can scan across those that pixel size, given your frame size. But it also will try and maintain the pixel dwell time as constant. So if I switch from 512 to 1024 and my pixel dwell time is approximately 2 microseconds, then it keeps that the same. So I always try and have a compromise between the speed and averaging. So keeping it around 2 microseconds pixel dwell time, I've been successful with, and doing an averaging of 2 or 4 if it's particularly noisy. But if you have a really bright signal, then you maybe don't even need to bother with averaging. But I think the reason why there's no hard and fast number is because you can vary so much depending on what your fluorescent molecule is and how many cycles it can actually go through.
Is there any reliable source or number that we can relate to our system for more common things like GFP versus some of these Alexa dyes versus?
Yeah. So with an Alexa dye or good fluorescent proteins like a GFP, I would stick with around a 2 microsecond dwell time. And I think that Zen usually sets you in that range. Anywhere between 1.5 and 2.5 microseconds is usually what it defaults to.
Is there a benefit to having the optimal setting would be like 2.5 times frequency instead of just 2?
So you want to sample at above 2. And my calculation isn't 100% accurate, it's actually 2.3 because the wavelength should be adjusted for your excitation and emission wavelength, so it's not quite as high as 2.5. And Doug and I were talking about this yesterday, that our non-physicist explanation of this is that if you have some signal and so this is the frequency that you want to sample, and you sample it at 2 times, you could sample it at twice the frequency of this and get a flat line. And so that would mean that you haven't sampled enough despite the fact that you've been 2 times the frequency that you're measuring, and so it should be above 2. Apparently this isn't actually true. This is oversimplifying at the level of physics, that I would need to invite a physicist up here to explain, but I think this is a somewhat reliable answer to that you want to be higher than 2, but it's actually not as high as 2.5, it's 2.3. Okay, thank you so much.